welcome to the class. If you're joining us remotely, and I see there is a, good morning, so feel free to enter your questions in the chat or call out to me. I think normally your microphone is turned off by default, but I think you have the capability of turning that on, or at least Arnaud did on Monday.
Okay.
Yeah, good. Otherwise, I'll try and follow the chat and make sure there aren't any questions in there. And oh, I have to share the screen. So you're there. Okay, so now I think
the screen is okay.
Good, thanks. And people here can see. So let's start with that exercise on page 31 that, remember I asked you to calculate the terms in the cross product using the tensor notation, and that in particular that alternating tensor, which might sound a little bit intimidating at first if you're not used to working with tensors. In fact, I claim you've all used tensors even if you haven't called them tensors, because even vectors are tensors. But I think it's nice to call things by their name and to appreciate the contexts or larger context for these tools. So let's well, maybe I can ask, are there any questions about that? Did anyone have any trouble? Did everyone attempt that? Yeah. Okay, good. If you like, I can go through it. What I thought I could do is just solve it here. Oh, is that right? Yeah. Okay. Exercise. Yeah. Well, maybe I hesitate to, like, I don't want to put people on the spot, but or make anyone feel badly, but is there anyone who didn't get the answer? Or are there people that want me to go through this and explain it? Is it sorry? Yeah, okay. So let me so yesterday in class I did the first component. So here, it's going to be a little bit tricky, but okay, I'm going to toggle back and forth between the two screens. So here's the actually, yeah, maybe the people at home can just be patient while I sometimes I have to re-LaTeX the other screen before it appears, before it updates. So just be a little bit patient if you're at home.
Okay.
Yeah, thanks. So we have this quantity WK that we want to calculate, and so it's a vector quantity because it has one index. So it's a type of tensor, but it's a special tensor. It just has one index. And that index K, it's understood that it can take 3 values to indicate the 3 components in 3-dimensional space. If we lived in a 2-dimensional world, which you can imagine sometimes you're just calculating things on a flat plane, then that index would just take 2 values. But in most engineering applications, we're in a 3-dimensional space. So our vectors have 3 components. So K takes the values 1, 2, and 3 to correspond to the 3 different directions. So let's start with K equals 1. Then we look on the right-hand side. That means we have to set K equal to 1 wherever it appears. It only appears in this third term, the epsilon ijk. So epsilon ijk, I defined earlier as this thing called the alternating tensor, which has the property that whenever the indices I, j, and k when any 2 of those indices are the same, then it equals 0. So for instance, if I equals 1, and j equals 1 and k equals 1, well, then we've got 3 that are the same, 3 indices. So that would be epsilon 1, 1, 1. It equals 0 because at least 2 of the indices were the same. So then I know that this term we know that this epsilon ijk is only interesting or only contributes to our sum when the 3 terms are different. Now we've set k equal to 1, and we want to sum over all the terms. So we know right away then that I and j have to be different than 1. So they have to be 2 and 3. So one of them's 2 and the other one's 3. So in fact, there's only 2 possibilities now. There's I equals 2 and j equals 3. And then the other possibility is going to be I equals 3 and j equals 2. So this, I forgot to mention, there's an implicit sum here over all the values of I and all the values of j. We don't sum over k because k is what we call a free index. It's not repeated. There's only 1 k. But here I see I twice. I see it there and I see it there. So that means I have to sum over I. You can think of this just, it really is just like a recipe book that we cook from, right? It's just follow the instructions and it'll all work out. And then you can reflect on it later to think about its meaning. Yeah, so we sum over I and j. We've set k equal to 1, and we've just said that I should be 2 and j is 3, or the other way around. So we have U2 times V3 times epsilon 1, 2, 2, 3, 1. Now we have to look up the values for the epsilon when it's 2, 3, 1, and you can convince yourself that this is an even permutation because I can get there by just, what did I do? I shoved I started with the permutation 1, 2, 3, and then I just shoved them all to the left 1 position. So the 2 took the first spot, the 3 took the next spot, and then the 1 had to go to the third position. So that's so we have epsilon 2, 3, 1 is an even permutation, so it's +1. So we have +1 times U2 V3. And so that gives us one term in the sum. But then we can, when we interchange the I and J so that it's U3 V2, well, I've just done one permutation, so I know that epsilon I JK has to be -1. Epsilon 3, 2, 1 is an odd permutation, so that's -1. So that gives us this first component that I've written here. Let me just LaTeX it so the people at home can see it. Yeah, there. Okay. Okay, so that gave us one of the three components of W, but K can take the values 1, 2, and 3. So let's move on to the K equals 2.
Should be a V2 on the second term.
Ah, thank you. Very good. Yeah, okay. And now, can someone tell me the next term? Minus U1 V3. Okay. Plus U3 V1. Okay. Let's have a look at that. So we, there's different ways we could arrive at that. Does anyone disagree with that? Anyone agree with it? It looks right to me. And so there's different ways you could get to that. One way is you could say, well, you could go through that whole argument that we just went through. Or another thing you could do is to just say, well, look, we increase the index K by 1. So we can just increase all of our indices in the first expression by 1. And we should arrive at the right formula. Now, if we increase, so we have a U2 here, so we increment it to U3. I have a V3 here, so I have to increment it by 1. But remember, it's cyclic, so that if you 1 beyond 3 brings us back to the starting point. By cyclic, I mean it's like the clock. You start at 1 and you go around to 12, and then if you go 1 more, or at least in the Anglo-Saxon world, you go back to 1. We don't talk about 1300. Well, they do in the military, but that not in everyday language. Yeah, so it's cyclic in that sense. So when you go past from 3 plus 1 brings you back to 1. And same thing with the U3 here. We want to increment that by 1. So we go back to U1. And if we increment V2 by 1, that goes to V3. So we could do exactly the same thing to get the final one. So we increment the K index by 1. If we increment U by 1, we should increment that by 1. And then that should go to 1. Let me just double check that that's right. Yeah, that looks right to me. Okay. So it's just, I think most of you are, yeah. maybe just to get, could I have a show of hands of people who sort of feel they're okay with this? And then can you, yeah, so most of you are okay with this, but so if you're, so I'm gonna move on. And if you're still working on that, you can read the notes but do ask me questions if you're still uncertain about that. I want to go back to exercise. I think I left you with exercise 2.1 at the end of last class because we didn't quite get to the end. So we had talked a lot about the stress tensor. And I wanted you to sort of see the stress tensor in some particular application. So I wanted to start with the simplest stress tensor you could imagine. And that's when the fluid is static. By static, we mean the velocity is 0 everywhere. So the tangential stresses, remember those are all the stresses are represented by this sigma ij, the stress tensor. Remember there were the ones on the diagonal that I wanted to call normal stresses, and the ones that are off the diagonal that I was calling the tangential stresses. Physically, the tangential means the surface, if it has a normal, say upwards, like the table, then a tangential stress would be pushing the table surface either to the left or to the right or forwards or backwards. So not in the direction of the normal. And so that's a tangential stress. And a normal stress is when you're pushing into the surface or pulling up on the surface. So your force is in the same direction as the normal to the surface. So these tangential stresses arise from the relative motion between different parts of the fluid that we like to call parcels. So there's relative motion between fluid parcels. Then there's that gives rise to tangential stresses in the neighborhood of this relative movement. So let's consider the simplest case we can, that of a static fluid. There's no, the fluid's not moving anywhere. And I give you that its pressure is little p. And I ask you for the matrix that represents the stress tensor everywhere in this fluid. And then I give you a hint here, because I realize it's not totally obvious, but okay, the tangential stresses must vanish. That means the off-diagonal components of the tensor have to vanish, but they have to vanish in all possible reference frames. Remember, I could always make those tangentials at a given point in the fluid. I can always choose my coordinates such that the off-diagonal terms are 0. So it looks like there's no tangential stresses, but that's because we've chosen our coordinates such that the stresses are either compressing or the opposite of compressing, elongating along special directions that we chose to line up with what the fluid's doing at that particular place. But here's the sort of subtle mathematical point, I guess, is that this implies if all those tangential stresses, so all the off diagonal terms in the matrix, have to equal 0, maybe I should point to a matrix when I'm doing this. If all these off diagonal terms have to be 0, not just in the special frame, but in all reference frames, that means that these diagonal terms have to all be equal. Okay, and if you're, how do you know that? If you're, I don't expect you to go into this level of mathematical detail, but I'm sure there's some of you who are saying, but how do you know that? So how do I know that? Well, it's because I know what this basis transformation matrix looks like. If you've seen a rotation of coordinate systems, it's just this matrix with cosines and sines, right? And so if you apply one of those, you pretty quickly see that if your diagonal elements are not all the same, you can create these off diagonal terms that are not 0. On the other hand, par contre, on the other hand, if you make those diagonal elements all the same, no matter what transformation matrix you apply here, this is a special matrix. It's something called an orthogonal matrix, this basis transformation matrix. So no matter what basis transformation you do, if those elements are diagonal, you're always going to have 0 as your off diagonal terms. If the diagonal terms are all just one number, if these, where'd it go? If these things are all equal, sigma prime XX equals sigma prime YY equals sigma prime ZZ, if those are all equal, then you can apply any transformation here and it'll always be 0 on the off diagonal. Okay. So that's the hint I'm giving you here. Yeah, so we require this thing here. So can someone, hopefully you've been working on this. So does anyone have the answer? What does the sigma, what does my matrix look like in this physical situation? Please call out if you have the answer. I think what I'll do is just type in the solution here as we go so that you guys have that solution. I check the chat, see if anyone at home has that. How do I find that chat thing? Oh, I go up there. Where's my chat? Oh. Okay. Well, let's go through it together then. So we want the matrix that represents sigma ij. So I'm just going to write it as sigma ij and then with the parentheses to indicate I'm talking about a matrix. And sorry, this is just a bit of LaTeX here. Yeah. Well, we know the off. I've told you that the off diagonal elements have to be 0. We know that the diagonal elements all have to be the same, and that this is related to the pressure, right? So it has to be some function of the pressure. But in fact, the pressure is a force per unit area, right? In fact, it's a normal force per unit area. So we just have to think carefully about the sign. So in fact, we suspect that this is related to the pressure. So if we just put pressure along the diagonal, we'll almost have it right. So I've just put pressure along the diagonal, but can anyone see any problem with that? Pressure is a force per unit area. Let's go back to the diagram. Well, it meets, let's first say what's good about this. We have sigma 1,1 equals sigma 2,2 equals sigma 3,3. And we have all the off diagonal terms equal to 0. So that's, and it's symmetric. Those are the three constraints that we know apply to this thing. And well, one thing we could simply do is apply this rule here. The pressure equals minus 1/3 of the trace. Okay, so if we do our trace here, we have P plus P plus P is 3P divided by 3 just gives us P, but we wanted it to be minus P, right? So we should put a minus here. That's the only trick, is the sign. And indeed, we can, I claim we can understand this physically as well, because the pressure is a normal force. It's a force per unit area. But remember the rule or the convention, I guess, when we were working these things out, we had say this is a normal stress here acting on the surface with the normal in the x1 direction. And remember the convention, we had to decide which fluid is acting on which fluid across the surface. So we said that the convention is, it's just a convention, but it's that we're going to call this the outside, or first of all, whenever you have a closed surface, that allows us to talk about the inside and the outside. And we point our normal, we had two choices, right? It can point to the inside or the outside. We choose to make it point to the outside. And then we say that this force that we're representing with the stress tensor represents the force of the fluid on the outside acting on the fluid that's on the inside. And we want that force to point in the x1 direction here for this particular one. But the pressure here of this fluid acting on that fluid on the inside is to push it in the minus x1 direction. That's what a pressure would do. And so we want the sigma, since it's representing a force in the plus x1 direction, or the sigma 1,1 here, is so that's where the minus sign comes from. in the pressure. Okay. Well, there's an example of the simplest form of the stress tensor. I understand it's a little bit, the notation is perhaps new and the notion of tensors, but this stress tensor really becomes quite useful. And so it's worth getting used to, because it contains all the information about these internal forces. So let's now talk about the viscous forces. The static and mechanical pressure, fluid pressures are not the only stresses in the fluid. We can have, especially when the fluid is moving, or parts of the fluid are moving relative to other parts of the fluid. The stress tensor is not isotropic. By the way, this is called isotropic because it's the same stress tensor in all, you could say, regardless of the orientation of the coordinate system. When you apply your this transformation matrix, which takes account of the fact that you've rotated your coordinate system, you'll always fall back on this minus p along the diagonal form here. So this is an isotropic tensor, and the tensor is isotropic when the fluid is static, but it's not necessarily isotropic everywhere when the fluid is moving. And indeed, it won't be in general. So the non-isotropic terms arise from the viscosity. And I mean, we're all familiar with viscosity. If you've watched honey flow or something, honey is a very viscous liquid. What is honey, or sorry, what is viscosity? Viscosity is it's the internal stresses that arise from the molecular transport, to transport on molecular scales or molecular forces. In the case of liquids, right, you can have hydrogen bonds within the fluid. That we have averaged out, so we don't deal with them explicitly, because we're treating the medium not as a collection of molecules, but as a continuous medium. We're modeling it as a continuous medium. So that's what that continuum hypothesis was about. But we have to recognize and take account of the forces that arose at that molecular level. And so that's what viscosity is going to do for us. Indeed, the pressure is doing something similar too, right? You could say the pressure, that one's a little bit more intuitive, like the pressure on this table due to the fluid here, the air is just literally the nitrogen and oxygen molecules bouncing off the table, right? That's and transporting momentum onto the table. So there's something similar going on that's on a molecular level that's creating, or something analogous going on the molecular level that's creating this viscosity. Yeah, I guess I'm actually learning more about, I'm getting into studying cell biology and stuff, and I'm learning about liquids are actually much more complicated if you look at them in detail at the molecular level, and you have these sort of temporary bonds that form. They're hydrogen bonds between the water molecules is what gives water some of its interesting properties. Yeah, so they're different than, of course, covalent bonds, which are like fixed and you need a chemical reaction to break them. The hydrogen bonds are, the water just flows and that forms and breaks new hydrogen bonds between the molecule. Okay, so that's a little aside on sort of the molecular origins of these forces that we want to represent in our continuum hypothesis. And so to get the correct mathematical form, I want to consider a simple experiment, which I think is quite intuitive and allows us to get the right answer in a very simple situation, which is then easy to generalize to the general situation, or general for what's called a Newtonian fluid, which is the fluid. Remember, on Monday I said we're going to deal with homogeneous, incompressible, and I probably used the word Newtonian fluids, or maybe I said simple fluids, but the simplification is Newtonian fluids, which applies to the atmosphere and the ocean. So it's a good approximation. And actually, the oils in your hydraulic systems should be Newtonian fluids as well. So it's really the exception to have a non-Newtonian fluid. Okay, so I'm going to consider a simple experiment with two flat plates parallel to each other, and they're separated by a homogeneous layer of fluid of thickness L. So the vertical dimension is going to be suppressed, just like I did for that other diagram I had, because it's much easier to show in 2 dimensions. So we're looking down on this, like the bird's eye view, we say in English. So you're like a bird looking down on this, looking vertically down, and we see 2 walls here. This black vertical line, I hope doesn't confuse you. It's just to separate. I have the figure on the left and the figure on the right. Okay, it was too hard to draw 2 separate figures, so I made one big one and then I cut it in 2 with this black line. So just look at the experiment on the left here. I've got this plate. Say this one's north of the one down here. So the north plate is moving to the east at a velocity u, and they're separated by thickness L here. And then I want you to try and anticipate. Well, we can argue based on the reconsidering the molecular origins of the fluid. We can argue that the fluid should be stationary with respect to the plate when it's for a thin layer of order of thickness, the mean free path, when the fluid is close to the plate. So here, we're in figure A on the left here, we're in the reference frame of the lower plate. So the lower plate is stationary. The fluid adjacent to that plate is stationary, and then but the fluid here near the north plate should be stationary with respect to that plate, so it should be moving in our reference frame to the east at this velocity here, the same as the velocity there. So these arrows in the blue fluid are representing what's called the velocity profile between the 2 plates. And I've chosen a pretty arbitrary profile here, and I want to argue that this is impossible, or this breaks some, actually in technical terms, it breaks Galilean invariance. So it doesn't obey the fundamental principles that actually go back to Galileo, the Italian Galileo. So how is that? I don't think Galileo studied fluid mechanics, but I'm just saying that I'm using one of his principles. So let's reanalyze this same experiment from the point of view of a reference frame of an observer, say, sitting on this north plate. So she would say that she's stationary with respect to this plate, but the lower plate, the south plate now, is moving to the west at constant velocity, the same magnitude, but in the westward direction. And if this were the velocity profile observed by the observer on the south bank, then the observer on the north bank would see the same velocity, or the velocity profile minus this, right? So so the velocity is 0 here. It has the same form, but it's just well, it looks like this. But then if you consider that the Galilean principle, or Galilean invariance, is that mechanical systems should have an equivalent description in different inertial reference frames, or even Galilean reference frames. That's why they're, I think in French you say Galilean reference frames, right? For inertial. I don't think we say that in English, but anyways, it's a nice term because it gives credit to Galileo for this. And so you see to be honest, I had to think about this a little bit to realize why this is a contradiction. But I guess the person on the north bank, they see the velocity sort of quickly increase and then sort of slowly level off here. Whereas this person sees, the person on the south bank sees that their velocity sort of slowly starts to drift and then rapidly accelerates. But that's a contradiction, right? Because they're both in some equivalent physical situation. They're just sitting on a bank with a plate opposite them, a distance L away, that's moving relative to them at constant speed. So they should see an equivalent situation. So you can, so I'm going to skip over all this text here, which just basically, I think, argues for what I've just said to you. And
just on the last version that you sent, we don't have the speaker.
Darn. Okay. So I better send that to you. Thanks for, I was trying to, I realize it's a bit annoying for you that I keep changing them. And so I'm sort of torn between this compromise of giving them it to you as quickly as possible so that you have it even ahead of time to look at it, versus, but then I'm going to change it, and then I have to keep giving you updates. So if you don't mind me keep, maybe the better sort of compromise is to give it to you regularly, and then yeah, then at least you have a version. And yeah, okay. So but if so we're searching for a velocity profile between these plates. By the way, this is called Couette flow. We notice that if we have a linear velocity profile, then then we've achieved Galilean invariance, if you like. There's a consistent description for an observer on the south bank and for an observer on the north bank. Okay. Which is kind of nice, because we've got this, there's a lot of complicated molecular motions giving rise to stresses that are adjusting the fluid velocity profile in here, and all that we've managed to not get into. We've just said that, well, we use some arguments about what happens at the plates to have what's called the no slip boundary condition. So the fluid has zero velocity near the plate within the molecular boundary layer. But other than that, we've just used Galilean invariance and arrived at this linear velocity profile, which is quite nice. And because it's a linear shear, so it's the velocity gradient here, the u velocity, so it's the u velocity that's in, say, the x direction. Say x is in the eastward direction here and y is in the north direction. Then my velocity gradient, du dy, equals a constant. That's what I meant by the drawing as a straight line here, and showing that the velocity increases linearly with distance from the plate, or distance perpendicular to the plate here. And it has to arrive at capital U when we've gone a distance capital L. So this velocity gradient is big U over big L. Okay, we can go into a little bit more detail. So imagine you're a fluid parcel in the interior. So you're, say, here, and you're moving along in the eastward direction. You see that parcels to your right are moving more slowly, so you're overpassing them. And you see fluid parcels just to your, so you're facing in the direction you're moving, right? So and so if you look to your left, that's to the parcels to the north, they are moving faster than you, so they're overtaking you on your left. So and that's true. I picked an arbitrary point in the interior. So at any point in the interior, you have the same situation. Fluid parcels overtaking you on your left, and facing downstream, and you are overtaking fluid parcels on your right. So there will be, we anticipate there will be these microscopic molecular motions that exchange momentum across the fluid parcels that cause a stress that ultimately leads to an exchange of momentum between the plates. So if this is a viscous fluid, there would be this lower plate will somehow exchange momentum with this upper plate. So there's some friction slowing this upper plate down, and vice versa. The upper plate will say that the lower plate is applying a friction force on the upper plate. So there's an exchange of momentum between them. That is a force that's proportional to the area of the plates. And the only stress profile that would not tend to change the velocity profile is a profile in which this force is this component of the stress tensor is a constant, which I'm going to define, or which has to be equal to the force per unit area. So this force per unit area is what we measure on the macroscopic scale between these plates, and this has to be related to the because ultimately it came from the internal stresses in the fluid, which were represented by this stress tensor, and the relevant term of the stress tensor is the sigma xy, because it's the force in the x direction on a surface with normal in the y direction. So if we just look at the say the lower plate, its normal is in the y direction, and it will experience a force in the positive x direction here, just intuitively, given the fact that the upper plate is moving to the right. And so it's trying to drag, the upper plate is trying to drag the lower plate along with it. So we anticipate a force in the x direction for that surface with a normal in the y direction. So that's the sigma xy term in the stress tensor. This force we would get from, the experiment, this force per unit area, but then we're going to relate that to the properties of the fluid by defining the dynamic viscosity as being the proportionality factor mu between the force per unit area and the velocity shear, or so the velocity, the change in velocity divided by the distance between the plates here. So that's a key concept. The dynamic viscosity is the proportionality constant between this force per unit area and the velocity gradient. So experimental data shows that for a wide range of fluids, so most fluids are Newtonian. Now this dynamic viscosity parameter it has to be stated for, different fluids have different dynamic viscosities, but this proportionality factor mu is independent of the velocity shear and other quantities related to the flow. It does depend upon temperature and pressure, most notably temperature, but you can, for most practical applications, there'll be some range of temperatures that apply. And if you have you can pick a typical temperature, and if the viscosity coefficient doesn't change too much, then you just use a sort of central viscosity coefficient that applies for the bulk temperature of the fluid. Okay, so we worked that out for a very specific controlled situation, but you can imagine that this we can generalize this to handle the most general situation. So our velocity profile didn't have to be uniform, but we can calculate the velocity gradient at any given point, and so the stress will remain proportional to the velocity gradient at that point in the fluid, And the proportionality constant between the two is this still the dynamic viscosity. And when this applies, we call it a Newtonian fluid. But all the fluids we're going to discuss are Newtonian. I guess the field of rheology deals with fluids that are not Newtonian. So some paints, I guess, are and complicated fluids are non-Newtonian and studied in the field of rheology. I guess that comes up in geology, right? You have complicated rheologies in maybe lava flows, or granular material. But we're going to, in the atmosphere and in the ocean and many engineering applications, they're Newtonian. So just to give you a general argument for the form of the relationship between the stress tensor and the velocity, you can show, or Bachelor in his textbook shows that the most general form of this relationship between the stress tensor and the velocity gradients would be a tensor relationship of this form. Don't worry, we're going to simplify this dramatically. This is just consistent with what we've said so far. We said that there's a proportionality constant that applies between the stress. Well, we worked with the case of stress x, y, or 1, 2, and the corresponding velocity shear. Yeah, so this coefficient here is representing the viscous properties of the fluid, and I've written it as a fourth order tensor because it has 4 indices, and the velocity gradients becomes a second ranked tensor because we can have 3 velocity components. So there's 1 index associated with the component of the velocity, and then we have the derivative of that velocity component, but there are 3 components of the derivative. So there's a 3 by 3 matrix here, which represents a second rank tensor. That tensor comes up over and over again in fluid mechanics, so it has a name. It's called the rate of strain tensor. So just the velocity gradient. And in particular, we're going to see it again when we drive the Navier-Stokes equations and we look at the acceleration of a fluid parcel. So this fourth rank tensor, it's explained by Olivier Arzel's notes, but also Bachelor's book. If we apply some symmetry arguments, we can show that for a Newtonian fluid, this fourth rank tensor A simplifies greatly to this form here. So they've broken it into 3 parts for us. We have the isotropic part that we've already seen related to the pressure. Isotropic because it's the, well, it's just that P along the diagonal, or minus P actually, minus P along the diagonal plus 2 times this dynamic viscosity coefficient times EIJ. So I'm going to explain EIJ in a second, in 2 seconds, and plus 2/3 times the dynamic viscosity coefficient again, times delta IJ, same thing we have here, plus EKK. So I have to explain EIJ and EKK. So EIJ is built out of this rate of strain tensor. In fact, it's called it has a name too, I guess, the symmetric part of the rate of strain tensor. And the way, well, this might ring a bell for if you've studied matrices and you've learned that any square matrix can be written as an anti-symmetric, the sum of an anti-symmetric part and a symmetric part. That might ring a bell, right? But if not, don't worry. It's all you need to know is that this EIJ that appears in this formula is defined this way. It's the the derivative of the ui velocity with respect to the xj component plus uj derivative thereof with respect to xi. So notice we've just interchanged the I and the j here. So that's why it's symmetric. So this EIJ, if we wrote it down as a matrix, the components off the diagonal are symmetric across the diagonal. So the one in the top right equals the one in the bottom left, etc. Yeah, so that's the EIJ. So EIJ appeared explicitly in this formula for the stress tensor, right? It was the 2 times the dynamic viscosity times EIJ minus 2/3 dynamics viscosity delta IJ times EKK. What's EKK? Well, now I have a repeated index there. And so I'm supposed to take the sum over the case when I equals J. That's what I mean here. So, well, when I equals J, then the term equals that term, obviously. So but there's a half here. So in other words, it's just the velocity gradient, right? It's just dek or diuk dixk. That's what the EI or this, I'm trying to build this term here, and then I have to sum over those. But when when I equals J here, we're talking about the diagonal term. So in other words, this EKK is this, it's the trace, right? It's the trace of this rate of strain tensor. It's the sum of the 3 elements on the diagonal of that rate of strain tensor. Does anyone know physically what that is? It has a name. Because this is the velocity, it's the divergence. It's the divergence of that velocity field. So the divergence comes up if you've studied electricity and magnetism, you talk about the divergence of the electric field, I think at some points. The divergence, now after, this is dangerous, I might say something that's wrong, but I think the divergence of the electric field is related to the charge, right? The charge density. It's been a while since I've studied that, so I'm not sure, but it comes up, right? In the electric, when you study electric fields, In fact, I have a suspicion that magnetic fields are divergent less. So the divergence of the magnetic field is 0. If I say any bêtises here, just correct me next day. But anyways, these I guess vector calculus quantities that you might have seen in electricity and magnetism are very applicable in fluid mechanics. And in fact, we're going to give a physical interpretation of that divergence term that we did, that EKK thing later. I think just before I leave this topic, I should define, we don't actually work with the dynamic viscosity that much. It's more common to work with something called the kinematic viscosity, because we'll see later that that's the term that enters the Navier-Stokes equations. So we take this, well, physically it was easier to introduce the dynamic viscosity mu, but if you divide it by the fluid density, then you get the what's called the kinematic viscosity, nu, Greek letter nu. And yeah, so let me just give you some typical values here. So if we have water, it's kind of interesting actually, because you think of water probably as being more viscous than air, right? But or that would have been my intuition. And that's true in terms of the dynamic viscosity, but not in terms of the kinematic viscosity. Because water is 1,000 times denser, or almost 1,000 times denser, it's when you divide by the rho to get the kinematic viscosity. So here's the kinematic viscosity in this final column here. It's something times 10 to the minus 6 meters squared per second. And it's still 10 to the minus 6 for air, but it's a little bit bigger, a few times bigger. So air is more viscous than water in terms of the kinematic viscosity. In terms of and that's the thing that matters in a sense. If you have a flow field, and you solve the equations that govern this flow field, it's the Navier-Stokes equations you're going to solve, and it's the kinematic viscosity, which is the parameter that enters the Navier-Stokes equations. So in terms of the dynamics of the flow, or maybe I should use the word kinematics, because it's the kinematic viscosity, but it's the governing equation. In terms of the governing equation, it's that determines the evolution of this flow. It's the kinematic viscosity that enters that equation, and water is less viscous, a little bit less viscous than air. So I said it's, you just prescribe typically prescribe a parameter for this kinematic viscosity, and away you go with your calculation. I guess in principle, if you wanted a very precise calculation, you would have to keep track of the temperature of the fluid and adjust your viscosity accordingly, right? Because it's changing a little bit. Say in water here between 5 degrees Celsius and 20 degrees Celsius, it changed, less than a factor of 2, but it changed noticeably. Yeah. Okay, so well, at the end of these notes, I have the books that I, yeah, in fact, these are all books that I cited.
Sorry, I've got a question on this for air, the viscosity. Also, something that's true. Is that true for liquids and gas?
Oh God, I don't know. Is the short answer to that. I think I can understand that now that I've never thought about this, and that's the first time I've had that question. It's a very fundamental question. But I think I could wave my hands and give an explanation for that. But how general that is, I have no idea. Do you have any comment on?
I was surprised because I understand that for liquid, the viscosity is like makes sense.
That makes sense. Why? I think you're right, or you're right. And but do you have an idea why? Or can you explain to us?
Because you are pushing the gas.
Yeah, I think what's going on is that the well, I haven't studied this, but just off the top of my head, the molecules are moving further apart, right? Because they're more agitated because they're at a higher temperature. So then the interactions between them are going to be weaker, just simply because the molecules are farther apart. Because the molecular origins of these forces are the it's the forces between the mostly electrostatic forces between the molecules. And even as I was mentioning, temporary hydrogen bonds between the water molecules. But with air, it's totally different, right? These because it's a gas, the molecules are mostly not interacting at all. They're only interacting for very short periods of time when they're very close to each other and they happen to collide. And so that the viscous parameters, viscosity, is related to the momentum transport, the momentum flux of the movement of these air, of the air. So and when it's warmer, it's they're moving faster, so they transport their properties faster. So like viscosity is a momentum flux, and the momentum flux is actually proportional to the square of the velocity, right? Because you have a flux that's proportional to the velocity, and then the thing you're fluxing is the momentum. So it's yeah. So this intuitively makes sense to me. So I guess insofar as that argument applies, then it's general, yeah. But I know that, but I'm learning more and more that water is actually, even though it's a very familiar liquid, it's a very complex liquid with lots of special properties. Like in the solid state, just a little trivia about water. Like in the solid state, there are many phases of the solid state. So they talk about ice 1 and ice 2 and ice 3. And these are like different crystal arrangements of the water molecules. So a friend of mine, actually, he worked on the so he uses ice core data, and he doesn't actually go out and get the ice core data, but he uses it. He uses the oxygen isotopes that they find in the little bubbles of air that are in the ice cores that you would find we talked about the Greenland ice sheet, and then there's the Antarctic ice sheet. So these things are great reservoirs if you're interested in sort of ancient climates. Like, how do we know the temperature of the Earth 15,000 years ago, or the concentration of the carbon dioxide in the air 15,000 years ago? It's actually wonderful that we have these ice cores or these ice sheets, because you can take by core, I just mean they drill a big tube down into the ice sheet to extract this long core, and they in there little ice bubbles, or little bubbles in the ice that are little reservoir, or little capsules that tell us what the air was like to 20,000, up to about, well, we can go back tens of thousands of years, and if you go back like 20,000 years ago, you can easily count the annual layers, right? Because you get annual layers of snowfall, and so it's like counting tree rings to know the age of the tree. Sorry, I'm really going off on a tangent here, but so my friend was using this data, so he's aware about the ice cores, and he heard that there are different properties of ice. So he did an experiment, and he put it online, where in his garage, he compressed the ice under a hydraulic jack and was measuring its density. And at some point there's this loud bang, and they didn't know what was happening at the time, but they realized later that it went through a phase transition. So the crystal arrangement of the molecules changed, and it went to a more compact crystal arrangement. So it transformed from, I don't know, ice 1 to ice 2, or ice 2 to ice 3 or something. Yeah, so water is a complicated, very familiar but complicated molecule. Actually, and this property, you've probably heard of this one because it's more familiar, but again, this turns out to be very exceptional. Yeah, just to sort of warn you or emphasize that we shouldn't extrapolate from water too much, because this, when the density of water, we have it here, it's increasing as we reduce the temperature, or the density decreases as we increase the temperature, right? But then there's this funny thing where if you reduce the temperature more, the density gets less. So there's, it's very counterintuitive. So this is for pure water, doesn't apply to seawater, but fresh water has this property where its maximum density is at 4 degrees Celsius. And so it stays liquid at lower temperatures, but its density gets bigger. So that's very exceptional. This would actually, we're a bit early, but this would be a good point maybe to take a break. And yeah, so let's meet back at 5 after 10. Okay, so yeah, so I'm recording it in case anyone at home doesn't make it, but also you can take advantage of that as well and watch these recorded versions of the lectures. I put it on YouTube. So you can find it there. Personally, I think it's better to just read the notes, right? Rather than hear me read the notes and try. I guess I try and embellish on them and explain it, but well, I'll leave it up to you. If you find my comments helpful, maybe it is useful to listen to the lecture again. But on the other hand, you can just read the notes and contact me directly or discuss it with your classmates. So let's continue. As always, feel free to ask me questions if you like. So I think, so at the start of each lecture, except the first one, I have summaries of the previous lecture. And so I guess I'm tempted to skip over that because I'm behind schedule, but maybe what I could do is go through it, but try and go more quickly. And yeah, so I apologize if I'm going quickly, but it's because we're actually behind schedule. So the key points of the last lecture is that we're studying fluid mechanics. It's a branch of classical physics, classical mechanics actually applied to fluids, which we approximate as continuous media through making this continuum hypothesis. We can define the fluid properties in terms of molecular averages, which is useful conceptually so that we know we have properties of the fluid as functions of position and time. And the properties we're interested in are especially the velocity, but also the density and the pressure, and in some cases the temperature. There are flows in which you don't care about the temperature and you can solve them as long as you have the other three. And in fact, for incompressible flows, we make the approximation that the density is constant. So it's just one number from the start. We're simulating water. We might say the density is 1,000 kilograms per meter cubed. And so the only dynamic variables, the variables that are changing with place and time, are the velocity and the pressure. We went into some detail into that, so we'd know when the continuum hypothesis, or to have some intuition about when we should be concerned about the continuum hypothesis. And it's whenever we think the mean free path might not be small compared to the length scales that we're interested in resolving in our flow. And formally, this ratio is called the Knudsen number, and it should be less than 1 part in 100 for typical applications. So we also just broke our forces in the fluid in terms of volume forces and surface forces, with a sort of practical definition that a volume force is anything that is most conveniently described as a force per unit volume. For us, the most obvious example, and perhaps the only example, will be the force of gravity. Surface forces are a little bit more challenging to describe. They're forces of molecular origin that are, most easily in our continuum hypothesis description, they're most easily represented as forces per unit area. And they're all described by this mathematical beast called the stress tensor. which is has two indices, so we can write it down as a matrix, and it's actually a symmetric matrix. So it only has 6 independent components: the 3 on the diagonal, which represent the normal stresses, and the 3, say, in the upper off diagonal terms, and which are the same as the 3 in the lower off diagonal terms, and which represent the tangential stresses. I think I reviewed today already the fact that we talk about forces and the convention regarding the force outside the on the exterior applying to the force on the interior. Our description was consistent with Newton's third law. So if we change the sign of the normal, it's the same as changing the sign of the force. It's not immediately obvious that that's true, but if you work through, well, if you accept that it's true, then you can convince yourself that it's consistent with Newton's third law. The pressure is defined as the trace of the stress tensor, minus 1/3 of the trace of the stress tensor, which is, trace is just a linear algebra term for meaning the sum of those 3 elements on the diagonal of the matrix. So the sum of the 3 normal stresses. And when the fluid is static, so its velocity is 0, then this trace of the stress tensor becomes the thermodynamic or static fluid pressure. The tangential stresses arise from the viscosity of a flow. For us, we're going to deal with Newtonian fluids, in which the stress tensor is related. Remember I said it's related to the relative motion. This equation 6 tells us exactly the expression of that relationship. So we have the pressure along the diagonal, minus the pressure along the diagonal, plus 2 times some constant, which is the dynamic viscosity, times the symmetric part of the rate of strain tensor, which is quite a mouthful, but it's, yeah, well, we can look up how to calculate it in any situation, plus or minus 2/3 the dynamic viscosity along the diagonal times, and then this EKK is a number that is corresponds to the divergence of the fluid velocity. So it's the trace of the symmetric part of the rate of strain tensor. In fact, it's the symmetric part of the strain tensor as well. Oh, and here I've written the symmetric part of the rate of strain tensor is written here in equation 7. So mechanical pressure, sorry, I'm getting it. That's the end of the review. And so now I'm gonna switch from overdrive to normal speed, but slightly faster than what I've been going up till now, because I'm a little bit afraid I'm going too slow. So we've talked about the thermodynamic. When I say thermodynamic, I mean it's the pressure that you've seen thermodynamics before, right? It's without going into detail, you need to know the pressure in a lot of formulas, and when they're talking about the pressure in the context of thermodynamics, like for an ideal gas, it's PV, pressure times volume, equals nRT, the gas constant times the temperature. And so that pressure there is the thermodynamic pressure. And it's the static fluid pressure. But when you have a flowing fluid, if you we have a stress tensor with a trace which is not necessarily equal to the thermodynamic pressure. And in other words, we have additional stresses that are related to the motion of the fluid. And those stresses can be tangential stresses, or they can be normal stresses. And so they look like a pressure, so, and they are a pressure. They're just different than the thermodynamic pressure. So we have a new name for them. We call it mechanical pressure. So we're going to write our, so that's what's going on physically, and mathematically we represent, of course, we always use our stress tensor to represent these internal stresses in a fluid. And in general, we can break this tensor into an isotropic part, so a part just along the diagonal with a constant times a constant value along the diagonal. That's going to be the big part of this tensor is going to be the minus the static fluid pressure along the diagonal, plus some departure from that or some additional term to finally arrive at this total stress tensor here. So this Dij is the what we call the deviatoric stress tensor. I guess that comes from the word deviation, so a variation from this isotropic part. And it's so if the fluid were stationary, if you could somehow bring the fluid to rest, the D would go to 0. And we would just have the static fluid pressure equal to the total stress tensor. So the D is due to the motion. What would we measure if we just stuck a pressure gauge in the fluid at some point, say Q, at some instant in time? Well, you would measure the average normal stress, which is given by the isotropic part of the stress tensor, which is not, if the fluid is moving, is not necessarily the thermodynamic pressure. So there can be a difference. And so the mechanical pressure that you would measure equals minus a third of the trace of the stress tensor. So the sum of the normal stresses in the X, Y, Z direction. And so that's the thermodynamic pressure plus this deviatoric or the diagonal part of the deviatoric stress tensor. So the mechanical pressure equals the thermodynamic pressure minus 1/3 the trace of the deviatoric stress tensor. Again, the D is because of the motion. So you only have this difference if the fluid is moving. Okay. So I guess that's a bit of terminology and well, and a bit of physics of thinking about pressure. How does this relate to the density Well, if you remember, pressure is a normal stress. It's a negative normal stress in the sense that the fluid outside is trying to act on the trying to compress the fluid inside. Inside doesn't necessarily mean a physical wall, right? We can make a conceptual boundary that we call a control volume anywhere we want. Right, so we're, and then we can think about we can define all these terms acting on sort of an imaginary surface there, and the pressure is going to try and squeeze some volume here, but it's going to squeeze a volume here. It's going to squeeze a volume anywhere, and in doing so, it will tend to increase the density because it compacts the fluid. So in fact, if I take the ratio of the increase in density, imagine I have the air in this room at 1 atmosphere pressure, and then we could somehow just increase the pressure in this room. We would, by a little bit, delta P. Well, that would tend to increase the air density in this room. By the way, the air density is about a little over 1 kilogram per meter cubed. It's kind of surprising how much air weighs. But if we could, so it's about 1.2 kilograms per meter cubed. If we could, at 1 atmosphere pressure, if we squeeze it a little bit, its density is going to go up a little bit. Let's call that delta rho. And let's divide that by the 1.2 reference density. So delta rho over rho. So I guess the fractional increase in the density. If we compare that to the pressure increase that we applied and also divided by rho, there's a proportionality constant there, which corresponds to the derivative of the pressure with respect to the density. So I guess this is just a differential calculus, right, applied to pressure and density. But we define a parameter called CS squared. And that turns out to enter the wave equation for compression waves in a fluid, and corresponds to this speed of propagation of these waves. So the speed of sound squared. Oh, that's true. Yeah, that's true. We could do that. Yeah. Okay.
Does it give something? It's not a bad comment. Just does it give something to keep?
Yeah. Well, I guess we're going to look at this quantity later. We're going to ask ourselves, what's the sort of fractional change in density, and I'm going to say how it's related to the pressure. Or actually, now that I think about it, it's the eventually we're going to talk about when is this quantity on the left-hand side big. Yeah, and so the speed of sound is going to intervene. Actually it'll become clear in fact soon. So the well, we're going to talk about it today and then come back to it later in 1 or 2 classes. So the but it's a good comment in the sense that there obviously we can cancel the density, and this equation would still be valid. So Yeah, so in this expression, I have the a change in the pressure. It turns out that you could work this out on dimensional grounds, that variations in the pressure are of the order of the, I want to call it the kinetic energy density. So it's the kinetic energy associated with the flow per unit volume. So if I take a volume of a unit volume of fluid, its mass would be the density. So it's mass per unit volume times unit volume gives me the mass times the fluid velocity. This is like mass times 1/2 the velocity squared, right? So this is the kinetic energy in Newtonian mechanics. And this kinetic energy of the flow is, well, U here is a typical velocity scale of the flow. So this quantity here, rho U squared over 2, is a typical kinetic energy of the fluid parcels. Per unit volume, and or for a parcel of unit volume, and so this you might expect that these fluid parcels sort of smashing around are what's creating the pressure variations. Or you might say the pressure variations are driving these changes in kinetic energy. It's either way you look at it, they should be of similar order of magnitude. So we want to replace delta P by a rho U squared over 2. And now my, yeah, so this is exactly the answer to the previous question. Now the rho cancels out, and so we have the variations in, or the fractional variations in the density are actually equal to 1/2 the Mach number squared. The Mach number is defined as a typical velocity scale of the flow divided by the speed of sound. Somewhere I must tell you the speed of sound. It's about 340 meters per second for air, and much faster for water, and I've forgotten now. I think it's 1700. It's at least 1500 meters per second, if not 1700 meters per second in seawater. So so it's convenient to describe flows in terms of their velocity scales relative to the speed of sound. So subsonic flows have speed less than the Mach speed of sound, and supersonic are between Mach 1 and Mach 5, and hypersonic apparently is greater than Mach 5. And notice that even if we have a 20%, or our Mach number is 0.2, which is starting to sound quite significant, 1/5 of the speed of sound, or 1/5 of 340 meters per second, I guess would be 68 meters per second, which is quite fast. But there are two things here: a square. So even if it's 20%, it becomes 20% of 20%, which is 4%, and then there's the half here, which knocks it down to 2%. So even at Mach 0.2, you only expect typical fluctuations in the fractional density to be of the order of 2%. Oh, here's the exact value, 341 meters per second at 15 degrees Celsius and 1 atmosphere pressure. Oh, sorry, it's 1400 meters per second in water. So all the currents in the ocean are, very low Mach number, essentially incompressible. And we'll look at some examples in the atmosphere. They have, in very extreme situations, you can have wind speeds that are not supersonic, but some significant fraction of the like more than half the speed of sound. But of course, they're very exceptional, like tornadoes. But just to be totally clear here, this is not to say that density variations are unimportant in the ocean. It's just to say they're extremely important. In fact, there are many important currents in the ocean which are related to the density variations, the famous thermal haline circulation, which is, a global circulation playing an important role in the climate system, under some threat from global warming. But the density variations that drive that thermal haline circulation and other important circulations are not associated with with the flow. They're not associated with, or they're not driven by this kinetic energy term here. They're driven by heat fluxes at the surface, something called brine rejection, like when sea ice forms, salt is ejected from the seawater, and that makes it denser, and then it sinks there. So there are density variations. They're important. We'll cover this in the ocean class, I guess, but they're not density variations that are associated with these with the inertia of the flow, and so they don't scale with 1/2 density times the velocity scale squared. Yeah, that gets, I mean, conceptually it's not complicated, but it gets subtle when you start being careful about the approximations you're making and putting in your equations. And so we'll get into that in the ocean class. Okay, let's move on to the mechanical equilibrium of a static fluid. So we're going to derive our first balance, the hydrostatic balance. So it's one of the most fundamental and useful balances in fluid mechanics. And we'll, we've rather than just give you the formula, we've gone through all the sort of background in terms of the stress tensor to really understand this in some detail. So in general terms, a static fluid must have a balance between all the forces, right? And we saw there are forces, are surface forces and volume forces. So let's, well, we're thinking whenever you hear volume force, you should probably be thinking gravity, right? But we're going to leave it general for now and just say I have a force Fi, or a force F, which is a force per unit mass. So I am thinking of gravity actually, but and then I multiply that by mass per unit volume. So it becomes a force per unit volume. And when I put the subscript I there, remember that means it's a vector quantity, and I'm just giving you the ith component, and I can be X, Y, or Z, or 1, 2, 3. And then I'm going to, we want to apply this to some body, right? Which is a general thing, but a closed, it'll be enclosed by some surface S, and it'll have some volume V. Okay, and in integral calculus, we learn that we can we want to sum up the force over that entire volume. So this is just a calculus, a differential calculus or an integral calculus notation of for breaking that sum up into an infinite number of little volumes of size dV, so infinitesimal volume dV, and doing a sum over that whole volume. So I think some of this, most of you, of course, have studied this, but if you haven't, you need to brush up on your this is differential and integral calculus. So this integral or sum over the volume V gives me the total body force over the body. So if this, so I'm leaving open the possibility that this gravity force varies a little bit with distance, or with the position inside the volume, and that the density is varying, but you know, the force of gravity per unit mass is about 9.8 meters per second, newtons per kilogram here near the surface of the Earth. So if we have even some rather large body here, that's going to be a constant, right? So we could just pull it outside of this integral, and then we just have the integral of the mass per unit volume integrated with respect to volume over the whole volume. We're just going to get the total mass of the body here. So it's just going to be 9.8 newtons per meter, or newtons per kilogram times the however many, the mass in kilograms. That's going to be our gravitational force, and it's pointed downwards, or this will be the non-zero, or that's the component Z here, with the horizontal component 0. And that has to equal, for each component, that has to equal the total surface, the forces acting on the surface of this body. So I'm going to do the same sort of integral calculus procedure of taking my surface and dividing it up into tiny little infinitesimal surfaces of area dA. And I don't think I've used this notation yet, but I've taken, normally that would be a vector dA, but I've decided to make dA a scalar, just the magnitude of the area, and then multiply that by the unit normal n. So that's my nj times dA is the vector area, or what I was calling the vector area before. And then that's multiplied by, remember, it's sigma ij gives you the force in the I direction. So the I here has to be consistent with the I there, so that we're talking about the same component of force. But then I have to sum over all the directions of j here, all the values of j. And so that I get all the different orientations, and we integrate that over the entire surface to get the total surface. So remember, we said that now we're keeping things simple and starting with a static fluid. So we know what this sigma ij is, right? That's the thing we worked out before the break. It was just minus p along the diagonal. Yeah, minus p along the diagonal of that 3x3 tensor or matrix, and 0 elsewhere. That's clear from the meaning of this. You have to memorize what delta ij is. It's equal to +1 if I equals j, and e equals 0 if I is not equal to j. So we're going to replace sigma ij with minus p delta ij here, which is what I did here. But now I'm going to sum over j. I've summed over j. This comments on the right tell you what I did to get from here to here, or what justified going from here to here. So I summed over j. It's just a pedagogical device that I either invented myself or stole from someone a long time ago, and now have forgotten whom I stole it from. But okay, so we sum over j, and of course this equals 0 except when j equals I. So now I just have this sum becomes ni, and then in the last step here, I have replaced an integral over the surface of the pressure times this normal vector, or unit vector normal to the surface, with the volume integral over the volume V enclosed by the surface S, with the derivative of this integrand here with respect to xi, the component in the direction of the normal. So that may or may not look familiar to you. Again, well, in English, we call this Gauss's theorem, the theorem that allows you to pass from there to there. Does that look familiar to anybody? Can you, just to help me know your background, who's seen this?
I just know about this. We can move from this to through some equation calculus.
Yeah, even if you know, you're saying you know it in some sort of vague terms, but yeah, that's okay. So you haven't seen this before in the back? I'm asking the gentleman in the, you have seen it. Oh, okay.
Yeah, long time.
Oh, okay. Okay. I asked you in particular because you seem to be following very closely all the steps. So I was a little bit surprised if you hadn't seen that, but okay. If the name is bothering you, that's because in the Anglo-Saxon world, we give credit to Gauss, and in the Francophone world, you give credit for some reason to Green, and who doesn't sound, neither of whom here sound very Francophone, but they're not French, right, that I know of, but yeah, just different, they're different traditions, right? And I find the mathematical world has a stronger sort of what do I call it? There are stronger regional differences. So in physics, there seems to be stronger mixing on an international scale. So physicists all over the world, doesn't matter whether they're French or Russian or American, they seem to talk more the same language, at least in my opinion, or my experience. But mathematicians are different. They like, so I said this to a Dutch mathematician, and he said, "What? Green Ostergrodsky, who's that, right? But I mean, he's taught longer than I have in the math department in France, in Brest. So for him, it's Gauss, right? Because he's part of the Anglo-Saxon tradition. So yeah, it's a bit funny. Anyways, it's nice that they are named after. You can't just call it the divergence theorem. When I learned it, it's also called the divergence theorem, because this, yeah, why is that I have to be careful. Yeah, but it's not divergence here, because it's a scalar, but anyways, yeah, so maybe Gauss's theorem is better, or Green Ostergrodsky. Anyways, let's not, this is an extremely useful mathematical identity that we're going to use repeatedly. I think you're going to see it elsewhere as well in fluid mechanics, so it's worth knowing, but we don't need to know it in more generality, and we don't need to prove it or anything, although I will give a sort of heuristic argument for it later. I'd like to just make a comment on the quantity in the integrand here in this equation 14. So we passed from, it's quite remarkable, right? We passed from a surface integral to a volume integral, but we changed the integrand from the pressure to the derivative of the pressure. In which direction? In the direction of this normal here, okay? We didn't change the sign or anything. So this is physically, I would call this the pressure gradient, right? Because it's the derivative of the pressure in all three directions. So it gives us a vector. There are three components of this quantity. And it has a physical interpretation. Minus the pressure, or minus this, well, if I just bring this negative sign inside here, I'd have minus the pressure gradient, and that minus pressure gradient has a physical interpretation. It's a force per unit volume due to the pressure variations in the flow. So if I have high pressure, at one point and low pressure at another point, I expect the fluid in between to feel a force directed from high pressure to low pressure, so in that direction. But the pressure gradient is a vector which increases in the direction of increasing pressure, so it points in the opposite direction as the pressure gradient force. So that's why you have the minus sign there. The minus sign indicates the force is from high to low pressure, but the pressure gradient is from low to high pressure. So I want to, so that was an aside on this surface term, right? Which we managed to rewrite as minus, or the integral of the pressure gradient force basically over the whole volume. And so we're gonna, but that whole thing is the left-hand side of that, or not the left-hand side, the second term on the left-hand side here in this equation 12. But now we have two volume integrals here. If we replace the surface integral with the volume integral, we have two volume integrals. So this is the second volume integral. So I can combine them into one volume integral. And this is really powerful, because now I use the fact that the volume that we started with was arbitrary. I didn't say anything about the volume. It didn't have to be a cube. It didn't have to be a sphere. It was just an arbitrary volume which enclosed us, completely enclosed by some surface. Yeah, so a volume completely within the fluid for this argument to work. So now I'm going to do one of those simple statements that there's actually a lot behind this. And, you know, I'm sure mathematicians have argued for hours about this, but it turns out that because this volume is arbitrary, it implies that this equation implies that the integrand has to equal 0. Okay. This one actually, I know a little bit about the history of it, and it comes up in a different context in Lagrangian mechanics, and Lagrange and others were like beavering away on this for, yeah, so it is true, but it's, you know, if that bothers you, maybe you're in good company, because it took a lot of very smart people a long time to know that this is rigorously true. And I'm not giving you all the mathematical conditions that have to be true in general to make this sort of step. But here in fluid mechanics, and for a wide variety of, or for regular functions that are the integrand here, then you can make this step. Actually, if you're ever interested in this sort of thing, you can talk to me about it. I think I could find a reference where they talk in much more rigorous detail. But for us, it's enough to know that this is these are physical quantities which vary smoothly. So we can, this mathematically, that means it's a regular function, and we can justify that step in saying that the integrand has to equal 0. And if the integrand is 0, then we have a differential equation here. We've gone from this difficult to use integral equation to a differential equation, where we just have the component of force. Actually, it's not even a differential. Well, it's just an equation which says the force here, the force per unit volume, force per unit mass times the mass per unit volume gives me a force per unit volume on the left-hand side equals minus the pressure gradient force. So that's equation 16. So that actually is what's called the hydrostatic balance if we make the physical interpretation about if the body force is gravity. But I'm getting ahead of myself. I'll show you that in a second. But this is our key result here. So I suggest we sort of pause and absorb that. So let's write it in vector form. How would that look in vector form? This is an exercise we can do together. We just have rho times Fi equals dp dxi. And then we're going to interpret it physically. I'll just pass to the solution there after you've thought about it. So this is all I was looking for, was this equation here, right? With F written with a little arrow, just recognizing that that's a vector. and that the pressure gradient is a vector. And yeah, I guess I'm realizing I was calling this the gradient. It's just the derivative of the pressure with respect to each coordinate here, x1, x2, x3, or x, y, z, which gives you a vector, right? I mentioned that when I was discussing the fact that this is a force. So the notation in vector calculus form is this del or nabla symbol beside p. Sometimes you see it with an arrow on top, right? To emphasize that it's a vector. Where I grew up in Canada, in physics, we didn't have, or engineering physics, we didn't have a little arrow there, but I've noticed in other contexts, people put a little arrow there, and it actually makes sense to me. It gives it more symmetry, right? It would sort of makes it more obvious it's a vector. So if you want to put an arrow there, that's probably a good thing. But I'm not going to do it because I haven't done it, and it'll be inconsistent. No. I also asked for the physical interpretation of this equation, right? So if we, so let's think about that. Where did it come from? So at the start we had some volume, it had a body force on it, and then it had a surface force, and we said, well, it's a static fluid, and we did all our approximations and did our integral calculus, and we came down to this formula. So what does it mean? Remember, we started from, we have a static fluid. So its velocity is 0, and it's staying that way. It's not accelerating. Well, we're saying that we also said that, I guess we used right from the start that it's a static fluid, and so we want the sum of our forces to be 0, right? So this is an expression of the fact that the forces are 0. So we have our body forces per unit volume times, or per unit mass times the mass per unit volume. So this is the force per unit volume. And we said that, well, we said the pressure gradient force, which we described physically, was minus grad P. So we're saying that the whatever volume force we have on there, probably the gravity, probably pulling it down, by definition, gravity pulls things down, has to be balanced by a pressure gradient force in the opposite direction, right? So the pressure gradient force, it's not that the volume force equals the pressure gradient force, it has to be equal in magnitude and opposite in direction. So the gravity is going to pull it down, and the pressure gradient, if volume force is gravity, and the pressure gradient force, I should say, is going to push it up. And the two are going to they have to be in balance for this thing to stay a static fluid. That's what we're saying. I'm just trying to think whether I give you, oh, I think that comes later. Okay, there's another thing I want to say about physical interpretation, but I think that comes up later. Or I hope I have my prompt to say that later. Yeah, so now let's assume that the volume force is what we call conservative. And well, here's what that means mathematically. Mathematically, that means that the force the ith component of the force can be written as minus the gradient, the d by dxi of some function phi, or sorry, psi, which is called a potential function. And I think there might be some discrepancy here between the mathematicians and the physicists, but I'm using the physics convention because the physicists want this potential to be the potential energy. And we want the potential energy to increase when you're moving against the force of the whatever's creating the potential. So that I think this minus sign might depend on convention, but in any world I've lived in, this has been negative. That's the convention. It doesn't really matter, but it's convenient to have the minus sign there. Yeah, I'm thinking I should say some sort of general remarks about when is this scalar potential, or when is a force conservative. Well, I don't want to scare you with it, but technically what it means is if the work done by the force in a closed path is zero, then it's a conservative force. Well, let me don't be too afraid if that's unfamiliar to you, but let me just say that the force of gravity is a conservative force. So we can represent the force of gravity by this scalar potential. In fact, previously when we said that gravity was about 9.8 newtons per kilogram near the surface of the Earth, we're effectively saying that the potential, the sun function psi here is just 9.8 times z, z being the coordinate. Because then when I take the gradient of that, if I take d by dx of that, I get 0. There's no gravity in the x direction. Similarly for y. But if I take d by dz of z times 9.8, I get, sorry, minus 9.8. I get minus 9.8. So that gives me the 9.8 newtons per kilogram negative, because it points in the minus z direction, points downwards. Yeah, so gravity is a conservative force that we can write in this way. But again, I guess I'm being general here, and so, but if I plug this in, this equation 18 into my tensor notation for the this balance here that we just derived for a static fluid, the static fluid balance, then we get this equation. And if we take the curl of this expression, so I guess I'm using vector calculus notions. So the vector calculus is in vector calculus, the curl is the cross product of this nabla operator with a vector. So I had a vector equation here, right? This is just the gradient of the pressure plus rho times the gradient of psi. I guess I'm talking in vector language because I thought that might be more familiar. But mathematically, I'm writing it in tensor notation because I think that's easier to use here. So these are just, you can forget that's a tensor if you like, and just say, well, I'm just taking, I have some pressure field and I'm taking the xi derivative. I have some psi function and I'm taking the xi derivative and I'm adding them together. And now I want to take the curl of this expression. So what do I mean by that? I mean, I take the, I take this thing is going to be my second vector. And the d by dxj is my first vector. And I'm taking the cross product between them. So I'm going to use this alternating tensor, which makes it convenient to do that. And remember, well, I realized as I was looking at this, I've used it in a slightly different way than I used before, but it doesn't change the number. You can, this thing's quite flexible. I just, if I want the ith component of this, of the curl of, well, the ith, I'm going to have a vector as a result, and if I want the ith component of the result, I can take epsilon ijk times d by dxj times or applied to this quantity with index k. Okay, so it's now, if you've studied vector calculus, you might remember notions like the curl of the gradient vanishes. The one thing I like about this tensor notation is that just, it doesn't become some sort of identity you have to remember. It just becomes something that is clear from the equations here. Or from the properties of the alternating tensor. So this is a linear operator. I can apply it to this thing plus the derivative of this thing. So when I have epsilon, so I'm going to have epsilon ijk d by dxj applied to this thing, right? And so that corresponds to in vector calculus, that's the curl of the gradient, right? But it equals 0 because I have, remember, when if I interchange j and k here in this alternating tensor, that changes the sign. But when I interchange the j and k here, it doesn't change the sign because they're, where did I do it? Well, here I have the another term, not for the pressure, but for the when I take this derivative with rho times psi d by dxk, I get two terms, right? I have by the product rule, I can take out the rho, and then I apply this derivative to just the d by d psi dxk. That's what I'm doing here. Let's just look at that term and we'll say why it equals 0. It equals 0 for the same reason that you have a 0 when there's a pressure, when the pressure is here instead of the psi. The reason it's 0 is because if I interchange j and k, epsilon ijk changes sign from -1 to +1, say. But this derivative doesn't change sign. So in other words, when you take d2 psi dx dy, that's the same as that gives you the same result as d2 psi dy dx. The order of these derivatives doesn't change the result here. And so, so I get both those terms, but I get -1 times it plus 1 times that. So they cancel. And so this thing equals 0. I can express this in terms of, you know, properties of tensors, if you like to, like the epsilon ijk is antisymmetric in J and K, and this this quantity here, the psi 2 dxj dxk is a symmetric tensor. So the product of the two summed over all indices equals 0. That's a general rule about products of this form. But since tensor calculus is a little bit new to you, I'm thinking maybe I shouldn't explain that in terms of tensors. I should just explain it directly for this particular case. I'm a little bit afraid that you're not following me, but just trust me, it's that one's, think about that later. If you're unclear about that, just try and work it out at home. I think it's not too mysterious. If you just think about the properties of the epsilon ijk and its symmetry properties, and the fact that this quantity doesn't change when you change the order of J and K.
Sir,
yeah.
Can I kindly ask you from time to time, try to help us please elaborate some formulas like these, I mean, these expressions. We work it together on the blackboard, something like this, in order to get exactly the steps, because I'm afraid I'm talking about myself, and I hope my colleagues here can join me. So we would like to see some formulas, how to develop some of them and get exactly how to get the results. So
yeah,
I'm asking from time to time if you think that we need to develop some expressions. Yeah.
Yeah, okay, that's a fair comment, and that's what I'm sure your colleagues would agree with you, or many of them would. So what I've done in previous years is, at this point, I would just go right on the board, right? But now we have these people at home, and they can't see what I'm doing on the board, and
I think they can understand the situation, and we will work it together with them. And, not a big issue. We are already in communication with them, and we share some of our notes. So yes, we can share that with them.
I don't mind.
you don't mind. Okay, thanks. I have one suggestion that I'll try this.
Me too.
Okay, but I think I have a suggestion. There's this whiteboard thing that I can share, right? And so let me try. It's a little bit awkward to use, but can you see the whiteboard at home?
Yeah.
Yeah. Okay.
Yes.
Yes.
So great. Okay. Let me do. So I had written this epsilon ijk. I'd written it ijk with the rho psi. I had written an J here, but I think maybe one source of confusion is that I changed that from the last, or no, sorry, that was, sorry. I had written as X J here, but I'm going to change it to I just because I realized that that's different than what I had done in when I first introduced the epsilon ijk. So where's my little pencil guy? Was it this guy or this guy? No, I had this like nice drawing tool, darn. Oh dear, draw. Oh, maybe it's this one. Yeah, oh, sorry, it's just that. Okay, so I'm going to, so this is going to give me the cross product. Maybe I'll write it in vector notation here. I'm going to take the cross product of that equation that we derived, which was what notation did I use? I'm thinking, yeah, so we want to write it in the no, we want to replace this to be rho grad psi plus grad p. Yeah, okay, I can do that. Rho grad psi plus grad. Actually, it's not so bad, this drawing thing. It's a little bit ugly, but it's you can read it, right? This is, so this is what I mean by the curl. I take grad cross some quantity that I'm taking the curl of.
Just a remark, because I found out, and maybe I'm not the only one, but when we test
Oh, yeah.
I did discover.
Yeah. Okay. Yeah, thanks for that translation. Yeah. So I can write the ith component just to be a formal here. I'm going to say I have some vector quantity here, and I want to pull off the kth element of that vector, right? So now I've made the transition to vector to tensor notation or index notation, and so I can write that formally as this epsilon ijk, and then I have to do my sum over the I and j, so I have to repeat the indices I, so I take d by dx I of the these vector quantities. Oh darn. Yeah, so I needed my gradient in there, and sorry, let me just, yeah, I'll just introduce another bracket here, and then have d by dxj of psi plus, oops, well, actually it's better to have the row there, and then d by dx j of p. So that's the jth component of this vector. To be correct, I have to get rid of that thing. And then yeah, okay. And then I take the curl of that. So I take the derivative with respect to xi. And then, yeah, okay. Are we all okay with that? So now this is distributive over this addition here, right? So I can just talk about the derivative of this term, and then I can talk about the derivative of this term with respect to xi. And of course, multiply it by the both of them by epsilon ijk. So let me look at this pressure one, because I didn't do that one in the notes. So let me actually, let me get rid of that and just focus on let me focus on this one here. Do I have room to do that? Maybe if I am a little bit careful with space, I can get it down at the bottom. So, so I have epsilon I j k, and of course there's a sum over j, or sorry, sum over I and j, and of d by dx I, but it's actually d by dx squared of xi d, or d squared dxi dx j. That didn't. Of p. So let me go up to the top and work out some of these terms, and we're going to see how there's two terms that cancel each other. Yeah, maybe just get rid of all that, because draw this thing. So let's say we can let k equal 1, for instance, and then we know when k equals 1 that for to have a non-zero term here, I have to have I equals 2 and j equals 3, or j equals 2 and I equals 3. So we're going to have for the first term, we're going to have that equals, I'll just write explicitly for k equals 1, just to be clear that that's the one I'm getting here. I have d by d x2, which is, let's just call it y, because that's what it is, and d by d x3, which is z of p. And that was a positive term, right? Because it was 2, 3, which is it was a 1, 2, 3, so that's a positive permutation. So I'll just be clear and write a plus there. But then we interchange the roles of I and j. So we consider the only other option when k is 1 to have a non-zero term is to have the 3 here and the 2 there. But then it's an odd permutation. So epsilon ijk becomes negative. So this is d by d z of d by dy of p. It's really ugly, but I think you can read it, right? So this is what I was trying to say is like here, the order of these derivatives, here I have d by dy of d by dz of p. And here I have the other way around. I have d by dz first and d by dy first, and then d by dz is applied first, second. But that doesn't change the value of this derivative. This thing equals that thing. Right, that's basic. Well, in English we call it the product rule of differential calculus. Now I don't know what you call it in French.
Since the Schwarz theorem, the theorem de Schwarz.
Theorem de Schwarz. Okay. 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 Could I say it's the rule of composite functions? Derivative of composite, or no, that's the chain rule. Sorry. Yeah. Okay, Schwarz. All right. So this equals 0.
I say that for English people, it's called Young's theorem.
Young's theorem. Oh, I haven't heard that. Okay, maybe that's for English people. I'm a Canadian English person. Okay, so this plus sign, just to be totally, well, I said this in words, but just to write it out, this came from epsilon 2, 3, 1 here, right? That's where I got the plus sign here. And then I got the minus sign for the second term because I was working out epsilon 3, I interchanged the I and the j. So I had a 3, 2, 1 here. That's why I had the minus, which is an odd permutation, which is why I had the minus sign there, right? So is this helping? Is this a sort of thing you were hoping I would? Yeah, okay, that's exactly what I sort of have done up until COVID-19 and the fact that I was afraid of using the board. Yeah, that allows me to show in more detail what I was trying to say. Okay, so that worked for the pressure term, right? And will you grant me that we had this sort of operator here hitting this gradient of the pressure? Oh shit! Or shoot! Let's stop this. Oh, I just have to go there, and then I make that big, and then I share, and then I'm back there. Yes. Okay. So so I was applying this what I would call the curl operator, which is the rotation thing. And and I applied it to this gradient of the pressure. We just went through that and said it was 0, right? Because of the anti-symmetry of the alternating tensor. But we have a similar term that's going to arise here because when we do the, because we have derivatives here, so we use what in English is the product rule. And so we hold the rho constant, and then we apply this derivative to this term, which looks just like this term, except it's not the pressure now, it's the psi. So again, that's going to equal 0. But the thing that's different is that we also have to apply this derivative to the rho. So then that's going to be different. And that's not going to be equal to 0. So let's work out that one. Well, here, I guess here's the answer, right? Is there anything to work out there? You apply this. Yeah, there's nothing to, well, I've written it here. When this derivative hits this term, we have the two terms, you hold the rho constant, and then you have something that looks just like the P, which we said was 0. The other term is when you hold this thing constant, the gradient of psi, which you see here, and then you apply the derivative, the xj derivative to the rho. So that's this term here. So that's all there is. And then we pause and then interpret what this means. Because now we have, I have a vector here, and I have a vector here, and I have the cross product between them. And I have that equals 0. So I think it would be useful to write that in vector notation. And in fact, that was the exercise. Yeah, so let's write that in vector notation. No, well, actually, maybe just before we do that, can I just say that, yeah, so this is just a hint to help you do that. Notice that here I've got epsilon I, like, let's look at the role of the indices in particular. Of course, it has the form of the cross product. Like when I introduced this alternating tensor, I said, this is useful for the cross product. Look, we can write the cross product this way. But then when I did that, I said, as I just did on that whiteboard thing, I said, let's find the kth component. And so we're going to have I be the first index on epsilon is I, and that was the first index on the first vector. And then the J is the second index on epsilon, and it was the index on the second vector. But now I've changed that here. So you should maybe note that, but it's not a typo. This is just it turns out that you can write it this way or the other way that I had it, and it works out to be, it works in both ways. maybe I can show you the answer that I was looking for. So I've written it here. I just wanted you to recognize that as the vector product or the cross product between two vectors. What are the vectors? The gradient of the density, cross product with the gradient of this potential function psi. So if we go back here just to see where I got that from, where did it go? Here. So it's the epsilon ijk with the d rho dxj. So that's the gradient of rho. This is the gradient of psi. And as I was saying, you have to make sure the indices are in the right places. But this works it works if this is giving me the first the ith component of a vector, and you know, the indices are aligned as they are here. So so that's the cross product of these vectors, and it equals 0. And what does it mean physically? Well, we have to remember that the cross product of two vectors equals 0. Well, if one of the vectors equals 0, the cross product with any other vector equals 0. So either there is no gradient in rho or psi, but if we accept that, well, the psi and rho are non-zero vectors, how could this equal 0? Well, it would equal 0 if there are density gradients and psi gradients. And there are psi gradients if there's a body force, right? And there are rho gradients if the density is varying throughout the fluid. And so what this says is that the density gradients must be parallel to the direction of increasing potential. But the direction of increasing potential is parallel to the lines, the body force, direction of the body force. So the density gradients have to be aligned along the line of force. It could be opposite, right? As long as it's parallel or anti-parallel, this equation will give 0. We can think of it also in terms of surfaces of constant density. Because remember, this is existing in a three-dimensional space. So if you have, say, density increasing in this direction, it means you have surfaces of constant density orthogonal to that density gradient. I hope you can sort of picture that. I didn't actually, maybe well, I was thinking I can go home and make a diagram of that with surfaces of constant density, and then the normal to it be pointing in the direction of the gradient, and those have to be those surfaces of constant density. Oh, sorry, I didn't finish the story. Line up with the surfaces of constant potential. So in geology, in the you call the geopotential, this gravitational potential of the Earth has a special surface of constant geopotential called the geoid, right? And that corresponds to the sea level. The mean, I mean, there are levels of constant gravitational potential surrounding the Earth, but the one that corresponds to the surface sea level is called the geoid. And so if the ocean were not moving, then this the water in the ocean would have to align itself so that the density surfaces were parallel to the geoid. And in fact, the air-sea interface is a if you think of the combined fluid of the ocean and the atmosphere as just different parts of the one fluid, but one very dense part and then a sort of light part above it. The air-sea interface should correspond to the geoid, and to a very good approximation, it is. In fact, I could give you the numbers. It's within a meter or so of the sea level. Mean sea level is within a meter of the geoid. There are variations, but they're there for good reasons, because the ocean is not a static fluid. It has current in it. I'm afraid I used up all the time today, and I wanted to get to the more concrete example. Maybe if you'll bear with me just a few minutes, I could tell you that if we replaced psi with the gravitational potential of the Earth, then this body force that we've been talking about abstractly would be the gravity of the Earth. And then this equation that we derived corresponds to the hydrostatic balance. So this says that the pressure gradient equals minus rho, the density of the fluid, times this 9.8. That's the equation that scuba divers would use probably intuitively when they want to know how much does the pressure go up as I descend into the ocean. So it turns out the density of seawater is 1,000. It's a little bit more than 1,000. I think it's on average about 1,035 kilograms, but say roughly 1,000 kilograms per meter cubed times 9.8 newtons per kilogram gives us almost 10,000 newtons per meter squared per meter, right? Per meter cubed, which is newtons per meter squared, which is a unit of pressure per meter. So then if we went 10 meters below the surface, we'd have 10 times 10,000, which is 100,000 newtons per meter squared over that 10 meters depth. And 100,000 newtons per meter squared is 100 kilopascals, which is close to the atmospheric pressure. So I think scuba divers would use a rule of thumb that says if you descend 10 meters, you get, that increases your pressure by 1 atmosphere. So all that comes from, but we derived that quite rigorously, right? Considering all the volume forces and surface forces acting in a fluid, and then we made the approximation that the fluid wasn't moving, that we had a static fluid. So we could throw out those off diagonal terms on the stress tensor and so let's pause there. I'll leave, maybe you can think about this exercise 2.3 for next week. I'll see you next Monday. Next Monday and Wednesday next week. Yeah, and please don't hesitate to contact me by email if you have any questions. In fact, I suggest you look at exercise 2.3 and exercise 2.4 because you have all the tools you need for exercise 2.4 as well. And there is the solution to the exercise immediately after. So in some sense, it's more a worked example, but just try and do it. And then if you get stuck, you can look at the solution that's in there. Yeah, and then we're essentially done that chapter.
So you should send us the new version.
Yeah, okay. Yeah, thanks for reminding me. I'll send you the new version of the. So bye-bye to the people in from home. Have a good weekend.